today we are going to have a new lecture section on the DRAM. So this is section 4. And this is the outline for the DRAM section. So first we will have an overview of the DRAM system, and then we will discuss the DRAM cell operation. So DRAM is based on one transistor, one capacitor. So it's 1T1C. And after that, we will discuss the DRAM device structure and the layout. So we're going to discuss different DRAM technologies, like the trench capacitor based or the stacked capacitor based. And after that, we will talk about two kinds of DRAM array architecture. One is called the folded architecture, the other one is open bitline architecture. And after that is DRAM scaling challenges. And since it's 1T1C, we are going to have discussions on the challenges of the capacitor first, and then the transistor. And finally, we will have some recent or future trends of the DRAM technology. First is the 3D stacking by the TSV, and embedded DRAM as well. So probably we will spend 4 lectures on the DRAM. Okay, so DRAM is short for the dynamic random access memory. So you have learned about the SRAM. So SRAM is static. So the difference is dynamic versus static. So dynamic means that we need the periodic refresh, and we will talk about that later. And the random access is the same as the SRAM. So each individual bit can be accessed, read or write independently. And again, the DRAM is volatile. This is similar as SRAM. So when you remove the power supply, the data will be gone. And if you compare the SRAM versus DRAM, so here we can have some different metrics to compare. So first one, the different applications. SRAM, as we know, we use for the cache, and DRAM we have more capacity, and we will use it as a main memory for the system. So the cell size, and we talk about the normalized cell area in terms of F square. And the SRAM, you know, is like 150 F square. And of course, if you size up the transistor W over L, then the cell size can be like 200 or even 300. But for the DRAM, it's quite compact. And here it shows 6F square to 8F square. So we will see that for today's mainstream DRAM technology, it's always 6F square. This 8F square is some old technology, maybe 20 years ago. But today's DRAM, all of them will have this 6F square cell area. So it's much more dense than the SRAM. That's why you can have larger capacity. And in terms of the speed, so SRAM very fast, right? So typically in less than 1 nanosecond. But the DRAM latency, typically tens of nanoseconds, maybe 20, 30, 40 nanoseconds. So we will discuss what contribute to the DRAM latency later. But DRAM is kind of 1 order of magnitude slower than the SRAM. And here's operation. SRAM is non-destructive read. DRAM is kind of destructive read. We will talk about this later. So when you read the DRAM cell, actually you are going to disturb the state, and then we need to recover the state. So we will talk about this later. And the leakage current. So the SRAM depends on what kind of transistor technology you use. Maybe high performance transistor or low power transistor. But even you use low power transistor, the leakage current is typically larger than like 1 picoamp per cell. This is limited by the off current of the logic transistor. But for the DRAM leakage, so here it's quite small. So like less than 1 femtoamp per DRAM cell. Femto, you know, is 10 to power negative 15. And this is because DRAM have this leakage problem, or this. That's why we need a refresh of the DRAM. So to minimize the leakage, then the DRAM transistor is a special transistor, and we will talk about that later. But this is different from the logic transistor. So this is different manufacturing process, different device structure. So even the foundry, I mean the manufacturer will be different. So the DRAM transistor is engineered for very low leakage to maintain the DRAM state. So this is like 1 femtoamp per cell. This is very small. And for example, one difference you can notice that the between the SRAM transistor and DRAM transistor is that the gate oxide thickness. So SRAM, is logic transistor. So and the T oxide probably like 1 nanometer. If you use silicon dioxide, if you use high K, then you can have the equivalent thickness. It's about like 1 nanometer or even below that. But for the DRAM, because we shoot for the low leakage and the transistor's gate oxide thickness is actually thicker, like 6 nanometer in this case. So this is a different fabrication process. So that's why the logic foundries like TSMC will not fabricate DRAM for you, because this is a very different fabrication process. Any questions?
So their oxide thickness is just 5 nanometer different, the process will be.
It's not only oxide, so this is just one aspect. So actually the transistor, we will look at that later, that it's very different. The shape and the structure is very different.
Is hafnium oxide also used here?
Hafnium oxide, yeah, probably. So for the high K dielectric, for the DRAM capacitor, hafnium oxide, zirconium oxide are typically used. Okay, so let's look at the DRAM from the system's perspective first. So let's look at the DRAM subsystem from the computer system point of view. And here we have some hierarchies, levels in the DRAM system. And this is from the top level down to the bottom. We have so-called the channel, DIMM, rank, chip, bank, and row and column. Or sometimes here between here we have another level called match. So here this is just a top-down breakdown of this DRAM system. We will talk about that in the next few slides. Let's look at the DRAM first. So you may have seen this before, and I actually bring one of this DRAM DIMM here, and I can pass around. You can take a look. So you may have seen this before, I think, and you insert this to the motherboard of your computer, and I can pass this around. You can take a look. I think this is one DRAM DIMM from Hynix, and it's like 4 or 8 gigabytes. So it was purchased a few years ago. So here, the DRAM subsystem, you look at this. So we have this data bus to the processor on your motherboard. And this is called the channel. And for example, this channel, of course, you can have different widths. For example, the typical like 64 bits. Of course, these days you have wider channel than this, but let's assume a standard 64 bits. And this channel can talk to multiple of this circuit board, and we call this DIMM, which I just pass around. So this is called the dual inline memory module, DIMM. So this is like one circuit board you can insert to the motherboard. And multiple of this DIMM can share one data bus. That means share this channel. So for example, in this figure, we have 2 channels. And each channel has 2 DIMM. Okay. So then, if we look into the DIMM, you will see, actually later when you see this DIMM passing around, you will see that on the DIMM, there are multiple chips. So here, those are the packaged chips. But sometimes the DIMM has 2 sides, the front side and back side. if it has two sides, then we call each side as a rank. But sometimes you don't have both sides packaged with the chips, so then you only have one rank. And each side you have this chip. This chip is packaged. Okay. And this is the chip and rank. And of course, this rank, you can see that there are pins here. In this DIMM, there are many pins. For example, there are maybe 100 pins. And later you can see that more clearly. There are many pins. So each pin will conduct the signal. And for example, if your channel is 64 bits, then you have at least 64 pins there. Of course, you may have additional pins for like control, but you will have 64 pins for the data to transfer. So that means the current really flows in and out from those pins to the package, and to the circuit board first, and then to the package, and then to the chip. So this is a rank and chips. So here this is again this rank. So from the memory channel, then you have the front rank and the back rank, and then maybe each of them will have 64-bit I/O, and then the total of the DIMM, you only have 64 bits. So that means you need to have a max here to select which 64 bits you need to get from the front side or the back side. Then each side will give you 64 bits. Then you select which one you want to choose. And then within one rank, then we have those chips. And typically we have 8 chips. And here, for example, each chip I/O give you 8 bits. And here you have 8 chips. So in total you have 8 times 8, 64 bits coming out. And within the chip, it is decomposed to multiple banks. Of course, here you cannot see it because it's already packaged. You cannot see those. But within the chip, you may have multiple banks. In this example, we have 8 banks. And then, for example, this 8 bits from each chip can be coming from either of those 8 banks. So each bank, for example, give you 8 bits. Again, you need to have a max. This is 8 to 1 max to select which bank you will get the data from. Okay, so this is a hierarchy. And of course, as we further look into the bank, then you can have those rows and columns. And in this example, we have 16K rows. So here we have 16K rows. And here the column, we have 2 kilobytes. Actually, you know, byte, if you convert to bit, it's actually 16 kilobits. That means 16 kilocolon. So the size of this bank will be 16K times 16K, will be 256 megabit. Okay. So sometimes this row, each row is also called a page. This is true for DRAM or for flash. And then again, we will have marks to select which columns you want to read the data from. sometimes this bank is too large, so we will break it into sub-banks, or sometimes we call it mat. So this is like sub-bank. So for example, in this case, this 256 megabit bank, we break it into many mats, and each mat, the typical size is like 1 kilo by 1 kilo. So you have 1 megabit, and one bank you may have 16 by 16 mats. So you totally have this 256 megabits. So this mat is the smallest array you will see.
Is it done for the fast access of the memory? Or is it done for the fast access of the memory?
Yes.
To get fast access to memory?
Yes, so the reason is, as you said, so if the bank is too large, then your word line or bitline become too long, then it will be slow to access the memory cell. So that's why we break up into those small mats. And typically like 1 kilo by 1 kilo, or sometimes 1 kilo by 512. So this is a typical size. And if you compare this, let's say this mat size of the DRAM compared to a typical SRAM array size, so do you think SRAM, the array size is larger or smaller than this 1K by 1K? Any idea? What is typical SRAM subarray size? Any idea?
Which smaller?
SRAM should be smaller because SRAM each cell is much larger, right?
Yeah.
So at the SRAM capacity, is much smaller than the DRAM. So SRAM typically like 64 by 64, 128 by 128, 256 by 256. That's a typical range. And here you see the DRAM, typically like 1K by 1K or even more than that. This is because each DRAM cell is much smaller than the SRAM, so you can have more cells along the word line or along the bit line. Okay, so this is the DRAM system. We have the different hierarchy from the top level channel to the DIMM, to the rank, to the chip, to the bank, and then to this mat. So any questions? Okay, then let's talk about the DRAM's I/O standard. So you may have read the specs of the DRAM, let's say in your computer or in your phone, right? We'll say it's DDR3 or DDR4. So what does that mean? So this actually is a standard of the I/O protocol. So DDR is short for double data rate. And here, from the DRAM array, or let's say from the bank, we can get the data, but there is a delay, right? As we discussed, the DRAM access latency maybe 40 nanoseconds. So then you can only access the DRAM after 40 nanoseconds. But we have the I/O, which is the input and output buffer. And then we have those I/O clock. So here we have two clocks basically. So within the DRAM array or DRAM bank, we have this internal clock. And this internal clock frequency is limited by the DRAM access latency. And in this example, for example, this internal clock frequency is 133 megahertz. And then as the I/O, there's another clock, which is I/O clock. So I/O clock frequency, okay, is what you can optimize for. Internally, the DRAM cannot be very fast. We will talk about why is that later. If you look at the DRAM operations later, you need to spend like 40 nanoseconds to read the DRAM cell. That will set up the maximum frequency you can have for the internal DRAM array. But you can have faster I/O clock. So the DDR is the double data rate. That means during the I/O clock, we are going to fetch the data in both falling and rising edge. So that means you double the data rate. Internal clock, you only get the data, for example, send the data to the buffer at the rising edge. But when the buffer sends the data out to the pin, for example, you look at that 64 pin on the DIMM, right? Those signals will run at double rate because those signals will have both rising and falling edge to fetch the data. So in this case, you double the data rate. So the data rate will be doubled. So will be 266 Mbps, bit per second. Of course, then you can increase the I/O clock frequency. You double the I/O clock frequency, and with a double edge, then you will times 4 of the data rate. And this is DDR2. And then DDR3, you will times 8. So this is the idea to increase the I/O bandwidth while keeping the internal clock frequency the same.
So aren't we using the internal clock frequency to fetch the data from DRAM?
We will talk about that in the second slide. So how does this work exactly? So the internal clock is slow, okay? You cannot do anything, actually. Even today with advanced storage, you cannot improve too much. It's like 200 or 300 megahertz at most. So the key idea is to do this so-called prefetch, okay? So for example here, we have this, for example, DDR3. I think this is an example for DDR3. So what you want to do is to prefetch the data from 8, for example, this 8 banks. So each bank you fetch 1 bit with this slow clock in parallel, okay? So you have 8 bit ready here after 1 internal clock cycle, because you get 8 bit from 8 different places. This is called prefetch. And then you have those 8 bit in the I/O buffer. You are going to burst those 8 bit out within 1 internal clock cycle with increased I/O clock frequency. So basically, here is a so-called serialized process, because this 8 bit is in parallel fetched. Later you are going to serially send the data out. So this parallel becomes serial in this DDR protocol. Any questions? So you prefetch the data from different banks in advance with a slow clock, and then you burst out with faster block at the I/O, because I/O only have 1 pin for those 8 bits. So this is 1 I/O pin. You can see that on that DIMM. So there's a limited space for the number of pins. So you have to serially send the data out, but with higher I/O clock frequency.
But how is the addressing done for like different banks? Like we would be sending an address from which we have to read. So if it's like available in the different banks, then how is the addressing handled?
Yeah, you can. The memory controller will deal with that. And that's not necessarily from different bank, or maybe from one bank different match. That's also possible. But the key idea is that you have to prefetch more data, let's say 8 bits in advance.
So you prefetch the data to I/O, then to the on-chip cache.
Yes, of course. I mean, if you use this DRAM in a computer system, then you know through the data bus, then you go to the on-chip cache.
Okay,
Yeah.
so is there like optimum number of bytes you prefetch that will give you the max like performance or something? Or
So this is limited by the number of pins you have, and you also limited by the clock frequency you can generate for the I/O. The higher clock frequency, of course, more power.
How do we burst the data after we prefetch it?
Yes,
How do we burst?
higher clock frequency in the I/O. Yeah, because internal clock frequency you cannot improve. You can increase the I/O clock frequency. So here, for example, here we can look at some numbers, so give you a better idea. For example, if your system calls for this kind of bandwidth, 12.8 gigabyte per second, if your system, that means your processor on-chip cache calls for this kind of bandwidth from your DRAM. And we know the DIMM, typically, for example, 64 pins, that means 64 bits, the data bus. So this is a 12.8 gigabyte, you need to times 8 to convert to the bit, and then divided by the 64 pins. So each pin, you need a 1600 megabit per second per pin. So this is the data rate you need from each pin. And the clock, internal clock, the core, this internal DRAM clock frequency is 200 megahertz. And you need the 1600 Mbps. That means you need to make the data rate 8 times larger. So that's why this is a DDR3 interface. So any questions?
How much energy consumption difference between DDR1 and
I don't have a number right now, but of course, as you expect, DDR, I mean, with higher number DDR3, DDR4, the power will be higher. So